Hello everybody, welcome to that tutorial. I'm Mohammad Abdulaziz and I will be your main tutor for the rest of this course. Today I will be performing a virtual tutorial where I'll be recording myself solving the exercises of the first sheet. Of course, if you have questions, you can ask about that tutorial on Piazza, and I'll either answer you there or answer you on BBB. I hope you all enjoy the course. So I'll start a tutorial. So the first thing before I would start any question, as written in the sheet, you are supposed to start an Isabelle theory file called x01 and put those 3 lines in it. So please do that. Pause the video and do that, and then continue it. So in this tutorial, I'll be the main goal is to really get you acquainted to the environment of Isabelle and also to let you prove your first theorems in it. And so the first thing I would like you to try is to use Isabelle as a calculator, really basically use its evaluation functionality. So as written in the sheet, I want you to try and evaluate 2 plus 2, for example, or 2 times 5 plus 3. Okay, so let us do that. Okay, so it doesn't, if we just write 2 plus 2 without specifying the number of, specifying the type of the numbers, it doesn't work, as you see. But when we tell it it's a natural number, then we get a 4. We can also do the second one, and it's the same. 2 that. So the output of either one of those evaluation functions is down there in the output panel here. Okay. So this is 16, as you can see, and the first one is 4. And the third one I will try also. So value of 3 times 4 minus 2 times 7 plus 1. So here this is this gives us 0, even though this should be like 12 minus 16. And the reason that is because these are natural numbers, so they go from 0 upwards, but there aren't negative values there. And that's why the subtraction here gives us 0. And in general, Isabelle's subtraction of natural numbers is defined to return 0 if you're subtracting a bigger number from a smaller one. So now that we have done that, I'm going to start the second exercise, which is stating natural number laws. So I will state the first one and prove it for you, and I recommend you pause the video and try to state and prove the second one. So the first law here we have is the law of commutativity of addition for natural numbers. Okay, so basically that law says x plus y equals y plus x. Okay, and we'll try and do that, but it doesn't work by O2, or we can say apply O2. It doesn't work because we didn't really specify the number, the types of x or y. So there isn't. So the addition is not. The addition operation here doesn't have the commutativity property if you don't for general arguments. It has it for natural numbers, for example. Then, so if we change that to not, apply O2 works, and then you have those goals, and the proof goes by. Okay. So now I recommend you pause and try to associate it for yourself, but I will So I will say associativity now. So associativity should be x plus y plus z equals x plus y plus z, but the parentheses are around the x and the y. Okay, so here again the proof goes by auto and we have no goals. So saying apply auto done, you can also just say apply auto and it's exactly the same thing. So now the third exercise, so you're supposed to define a function which counts the number of occurrences of a particular element in a list, okay? And that function should be implemented should be defined as a recursive function on lists. So the function will be given a list of type of type alpha list, which means that all of its members have some type alpha, and the second argument which is an element of type alpha, and it returns a natural number, which is the number of occurrences of the second argument in the list. Okay, so I'll write the signature and then I recommend you pause the video and try to define it yourself before watching me doing it. Okay. So zero type is alpha list takes alpha and returns a natural number. Okay, so pause the video now and try it without. We'll continue. So count. So the first case will be like when the list is empty, and here, regardless of the argument that we have, we should return a 0 because the empty list has 0 elements of any, has 0 elements, and that's it. And the second case will be the cons case. So we have x at the top of a list x's, and we want to count the number of occurrences of an element x prime, and that should be if x equals x prime, then successor of count x's and y, otherwise we return just count x's and x prime. So that should be an x prime as well. Okay, so successor here as just means the next natural number, or the natural number. Successor of a natural number is just the natural number plus 1. So that, so that's what that means. So if we write that, so now if we want to test our function, we can try it on a few examples by using again the value functionality. So you can say, for example, value of count of empty and 0. Okay, it will not work. You have to give it. You have to identify the natural type, attribute type for the elements of the list. So here we're saying not natural numbers. So the empty list has 0 elements that are equal to 0, and this list also has 0 elements that are equal to 0. But if we add a 0 at the end, we get a 1, and if we add another 0, then we get a 2. So the function seems to perform correctly. So now our next task is to prove that the function satisfies this inequality. Basically, that the number, it always returns a number that is smaller than or equal to the length of the length of the given list. So I'll specify the theorem, and I recommend you pause the video and try to prove it yourself. and I'll give you just a hint, so you should try to prove it by induction on the list x's. So you can pause it now and try, and then I'll do it. So if I say induction x's, what we have here is two cases. So the base case, count x of empty and smaller than or equal to the length of empty. And when we define that function, we had equalities that correspond to the different cases of the function. And one of those equalities is the count of anything in the empty list is equal to 0. So if we do apply auto, apply simp, it will substitute that with 0 from here, and also where the function length is defined, I will just go there. It will you will find also a rewrite true an equality that says the length of an empty list is always empty. So if we do apply auto, it will do that for the first case. And before I do apply auto, I also want you to just study the induction hypothesis for the step case and the goal, and see how it will be used. So here, when we say count of x and in x's less than x's, that is the induction hypothesis. So we want to use that to prove this goal. So basically, we want to prove to transform this goal in a way such that this could be immediately substituted for in the goal somehow. So what we want, so we have here count a cons x's x. Okay, so we're counting the number of elements of in this list that are equal to x. Okay, so if we say apply auto, it will apply an equality that corresponds to this case. So it will give us two cases. If x equals a, then it will just be the count of x's. So if x equals k, then this thing equals just count of x's. Sorry, if x is not equal to a, then this thing, this highlighted thing will be equal to count of x's and x only, based on that second equality there, the second case here. And then from the induction hypothesis, we have that count of x's and x is less than length of x's. And also auto will be able to say that the length of a cons x's is length of x's plus 1. So you will be able to show for the case x is not equal to a, that count x is less than length of x's plus 1. For the second case, which is if x equals a, then the equality, this will this side of the highlighted term will be substituted substituted for by suc count x's and x. Okay, so basically, so here you have suc count x's of x, and here you'll have suc length of x's, and here in the induction hypothesis you have that count of x's of x is more than or equal to length of x's, and that will and there is a theorem that O2 there's a theorem that O2 will use that tells it that tells it if a is less than or equal to b, then suc a is less than or equal to suc b. So I just told you what O2 will do, and it does it magically, but you will sometimes have to understand the induction, especially the step case, and do analyze it. So that's why I was analyzing it, even though auto will do it automatically. So an alternative syntax for that, you can just write by induct x and then auto, and that's it. So this is exactly equivalent to apply induct x and then apply auto, and then done. So now we're done with the first thing. So now we'll start with the fourth exercise. So here we're required to define a function that adds an element given a list and an element, adds that element to the end of the list. Okay, so there is already a function to append two lists together, but we're not supposed to use that to define snock. Okay, so snock is a function taking a list, an element, and adding that element to the end of the list. So I'll write the signature now, but remember it has to be recursive on the list. You shouldn't define it using that append, that existing append operation. Okay, so the signature is snock alpha list. Okay, so I would recommend you pause the video and try to define it yourself, but I will continue. So snock of element of the empty list and an extra element should be equal to the singleton list with that extra element. And the second case will be, so I'll just call that x prime again, just to be consistent with the previous case. And the second case will be snock of x and x's and an x prime. So that is slightly tricky. So it should be, yes, exactly as you guessed, x prime cons snock x's, sorry, this should be x, x's and x prime. Okay, so this basically we're taking here we're taking all the elements of the list one by one and putting them at the top until x prime is left and the list is empty, and then we add x prime as the last element. So, so again, to convince yourself that this is the function that we wanted, we just will evaluate. We'll try and evaluate it on a few examples. So one, for example, 2 and 3. So those are a list of 3 elements, and then we want to add to it the element number 4. So it works well, so that's what we wanted. Also an interesting thing that is to make sure that this evaluation is actually correct, you can prove it as a lemma. You can prove that, for example, here snock 1, 2, 3 and 4 is going to give us the list of 4 elements. You can, when we write it as a lemma like that, we know that there is no we know we have it as a theorem, and that is, for example, in the homeworks a lot of times I will give you a task of defining a function and proving some theorems about the function, and the way I will test your definition is by putting lemmas like that one there. So the function that you defined on some argument equals some output that I know is, and these should be test cases. So here that is the corresponding lemma. So we have that by sim or by auto. Like many methods can do that. So here we just are sticking to auto. Okay, so define the. So now we define that function, and then we need to use it to define a function reverse that, given a list, returns that list in reverse order, and then we can do that we need to do that recursively using the function snock that we just defined. Okay, so we'll write the signature, and as usual, I recommend you pause the video and try doing it yourself. That is the signature. I recommend you pause now, but I will continue. So reverse, the first case is, of course, the empty list. and then reverse that case. Should be equal to snock, so we basically just add this element at the head of the given list to the end of it. So reverse x's and add that there. Okay, so that is the function that we want, and again I will try and make sure that it works on a few of the examples. So first 1, 2, 3, 4, and let's say that first element type that. Then missing semicolon. Okay, so 4, 3, 2, 1. So it seems like it works. And again, you can also prove that as a lemma. But the more interesting part is proving that this function does what we want. So, like proving one feature of this function that assures us that it does what we want it to do. And that feature is that the reverse of the reverse of a list is the same list. So I will write the theorem here. And yeah, I recommend you try and do it, and it should be done by induction on x's. I will continue now, but you should pause and try it yourself first. So apply induct x's. Okay, and then we have the base case, and that's easy because we have the reverse of empty is equal to empty. That this will be substituted by empty, and then this will be substituted by empty, and then it will be done by O2. And this one, yeah, I will just apply O2 and see what happens and try and analyze the step case. So here, now the step case that is left to us is reverse x's equals x's. So we need to change that, the conclusion of this goal that we have here to match reverse x's. So what that means is basically we need to get this knock out there, okay? And one way to do that is to prove an auxiliary lemma that can help us prove this theorem. That basically that can get this snock out there. Okay, so I recommend you try and you stop the video now, or you pause the video now and just try and guess what this lemma is. But I will just write it now. Okay, so a lemma, such a lemma would be reverse snock, that's what I will call it, and what we basically want is reverse snock x and x equals. So you know, you can also just get that lemma. You can actually, a lot of the times you can just copy what you want to modify it. So that's we want to change that conclusion of the goal. Okay, in order for it to in order for the induction hypothesis to be used, and what that means is that we want to get this knock out there. So what we want to do is that snock of the reverse, or another way to do it is, I don't think we can actually get the snock out there. Well, another way to do it is to change the snock into a cons outside there. So basically, when we get this snock outside there, it should be changed into a cons. So if I say reverse of a list, just any list wise reverse of snock of a list y is an element A, for example. Okay, it should be equal to A cons the reverse of this y's. Okay, and this way, when we use that induction, when we use this lemma, when we use this lemma here, it will rewrite. It will be like if we give this lemma as an argument to simp, it will transform that part of the goal into an A cons reverse of x's, and then reverse of x's can be used to write that write that. So can be used to write this left hand side and turn it into just x's, and then you will have A cons x's equals A cons x's. Let me write that there. Let me just try and prove that there first. So this should be also proven by induction on y's. Let's see if it follows. So it goes. Okay, so now the next thing is to give this lemma as an argument to auto in order for it to be able to transform that sub goal. Okay, and the way I do that is, for example, you can say auto simp reverse snock. Okay, and that does it. So this basically tells auto that you can use reverse snock to substitute terms in the goal. And now we're done. Another way to tell auto that it can use this lemma to simplify is to actually just say here simp, and then we don't need to give it as an argument to auto. So now we also have the same thing. But in any case, the most important part in this is that you understand how to analyze your induction hypothesis and come up with the right lemma for you to be able to use the induction hypothesis. Okay, so that's it. Thank you very much for listening to the tutorial, and I suggest you go to the website of the course and read about the competition system on which you're supposed to submit your homeworks, and please register there. And if you have any questions, please post them on Piazza. Thanks.